So in the last lecture, we have defined the for a vector space V, for a vector space V, and if we suppose that S be a subset of S V, then the linear span Ls of S is the smallest subspace of V containing S. And we have proved this result in the last lecture, that linear span of S is the smallest subspace of V containing S, which has been defined as the smallest the subspace generated by S. Yeah. This. For example, if we are in the plane that is in R2, so if we consider R2, then one can observe that the set 1 0 0 1, this set will generate the whole plane. R2. So R2 is the linear span of this set. In a similar way, if we go to the higher dimension, higher space, that is R3, R4, although I have not defined dimension, but I am so whenever I am calling that it is of dimension 3, that means it is R3, R4. That. So if we go to R3 in a similar way, the set 1 0 0 0 1 0 0 0 1, this set generates R3 and so on. That is, if we go to R4, then you will definitely have a generating set, that is 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. In R5, just doing the same thing as in the lower cases. Also, apart from these sets, in R3, you will also have, suppose if we consider a set, suppose S consists of the vectors 1 1 0, 1 0 1 and 0 1 1. Then if we consider an arbitrary point in R3, then we see that XYZ can be represented as lambda 1 1 1 0 plus lambda 2 1 1 0 1 plus lambda 3 0 1 1, where lambda 1, lambda 2, lambda 3 are three scalars, and which can be determined by the three equations, which are, that is, from this part we will have, this is lambda 1 plus lambda 2, which is x, that is lambda 1 plus lambda 2 is x, where lambda 1 plus lambda 3, it is y, and lambda 2 plus lambda 3, it is z. It is z. And then by solving these equations, you will get that lambda 1 will be half of x plus y minus z, lambda 2 will be half of x minus y plus z, and lambda 3 will be half of minus x plus y plus z. So in this way, we can represent any point in R3 as a linear combination of these vectors. So which says that this S generates the whole of R3. So that means the linear span of S will be, so that is linear span of this set 1 1 0 1 0 1 and 0 1 1. This is actually the whole space R3. Yeah. You can also check this one. Suppose you are considering the space M2R, that is the set of all those 2 cross 2 matrices over the field of reals. And then, that is, suppose V is the space of all 2 cross 2 matrices with real entries, and let S be the set of all these matrices, that is of the form 1 1 1 0 1 1 0 1 1 0 1 1 and 0 1 1 1. So as in above, you can easily show that any matrix of this space will be a linear combination of the vectors of S, just by taking any matrix A B C D belongs to M2R. We have, suppose that ABCD can be represented as a linear combination of these matrices, that is lambda 1 1 1 1 0 plus lambda 2 1 1 0 1 plus lambda 3 1 0 1 1 plus lambda 4 0 1 1 1. While lambda 1, lambda 2, lambda 3, lambda 4 are 4 scalars. Now doing the matrix addition, you will get a matrix of this form, that is lambda 1 plus lambda 2 plus lambda 3, lambda 1 plus lambda 2 plus lambda 4, lambda 1 plus lambda 3 plus lambda 4, and lambda 2 plus lambda 3 plus lambda 4. And again, by equating the same entries, you will get 4 equations, and ultimately By solving these 4 equations, you will get that alpha 1 is lambda 1 is 1/3 of a plus b plus c minus 2d. Lambda 2 is 1/3 of a plus b minus 2c plus d. Lambda 3 is 1/3 of a minus 2b plus c plus d, and lambda 4 is 1/3 of minus 2a plus b plus c plus d. So in this way you can show that any matrix of M2R can be represented as a linear combination of the matrices considered in the set S. These 4 matrices. So therefore the linear span of S in that case also. So therefore linear span of S is M2R. Yeah. Now our above examples give us that the linear span equals with the whole space. But if you consider the vector space M2R again and just taking the set S star equal to the matrices of this form, that is 1 1 0 1, 1 1 0 1 0 0 1, 1 1 0 1, and 1 0 1 1. Just considering these 3 matrices in M2R, then the linear span of a star, what will be that? That is the linear combinations of these 3 matrices, that is of the form lambda 1 1 0 0 1, lambda 2 1 1 0 1 plus lambda 3 1 0 1 1, where lambda 1, lambda 2, lambda 3 are any scalars. So therefore this linear span will consist of these matrices which looks like lambda 1 plus lambda 2 plus lambda 3, lambda 2, it is lambda 3, and again lambda 1 plus lambda 2 plus lambda 3, while lambda 1, lambda 2, lambda 3 are real numbers. So the remark is that one may find different subsets in a vector space that generate a subspace, a linear subspace W of the vector space. Of the vector space V. And so it is very much natural to look for a subset of W that generates W and is as small as possible. That is, we need to find out a subset for that subspace, this W, that we have generated by some subsets of a vector space. Now we need to find out a subset that generates W and is small as possible. Okay, so that is our aim. That is, we need to find out a subset which is as small as possible. So we must concentrate. So we must concentrate on removing a vector from a generating set of vectors of a subspace W to achieve a smaller generating set. That is that what I want to tell you, that let S generates W. Now we need to find out a smaller subset contained in S which also generates W. That we need to find out. A smaller subset of S which also generates the subspace W. So that is our goal. And the way of finding out this subset of S that generates W is to remove a vector from the set S to achieve a smaller generating set of vectors of the subspace W. That is, we need to delete a vector from S which generates W. So this is our way of finding out this minimal generating set which generates W. So let us find out how to do this. So before going to do before going to search out such minimal generating subsets of a subspace W, we first define quotient vector space, which will help us to do the job. So let us consider a vector space V over a field F, and also let W be a subspace of V. Now, since V is a vector space, so with respect to addition, it is an abelian group. And for that reason, W being a subspace of V, so it must be a normal subgroup of the additive group V plus. So W is a normal subgroup of V plus with respect to addition. And so we may consider the cosets, which looks like, so consider the cosets small v plus W. So which looks like V plus W, because our operation is here addition. So that is why we are writing down a coset like that. And then we set V slash W equals to set of all these quotients where V belongs to capital V. Now, this set, so we are to equip two operations. One is vector addition and another is scalar multiplication on this set, induced from the additive and scalar multiplication operations of V. And the way of defining this is like that. For any two cosets, suppose one is V plus W and another is V dash plus W, then belongs to V slash W. We define v plus w plus v dash plus w. So the definition is v plus v dash plus w. So the sum of these two cosets will be the coset v plus v dash plus w. And next, scalar multiplication. Now, what is scalar multiplication? Scalar multiplication. As V is a vector space over the field F, so we need to consider the same field to define the scalar multiplication on this set. So for that reason, let us consider a scalar alpha belongs to F and a coset belongs to this set. Then we define alpha dot v plus w has been defined as alpha v plus w. Now this alpha v, this is due to the scalar multiplication of the vector space V. So this is alpha v plus w. And this is your exercise to check that these operations are well defined. Well defined. So, what is the reason? For any two. So, how will you do that to show that the operation is well defined? So let us have a look on the scalar multiplication. So suppose we are considering two cosets. One is v plus w, another is v dash plus w, but we suppose that these two cosets are same. If they are same, then if we multiply scalarly v plus w with alpha and vs plus w with alpha, then again the cosets, the resulting cosets will be also same. That is, if we consider these two cosets which are equal and for any alpha belongs to F, we have. Now since these two cosets are same, so then this implies, so V dashed minus V must be in W. This is a basic result of cosets. That is, they are in the same class. So V dash minus V belongs to W. Now since W is a subspace, so being a subspace, if we multiply alpha with this, then we will have alpha V dash minus V also in W, as W is a subspace. So here we see that the need of considering a subspace of a vector space. This implies, so alpha V dash minus alpha V belongs to W. That means alpha V plus W equals to alpha V dash plus W. So these two cosets are also same. That means alpha V plus W means alpha dot V plus W, and alpha V dash plus W means alpha dot V dash plus W. So this proves that the scalar multiplication that we have defined above is well defined. So thus the operations defined on V slash W, these are well defined operations. And with respect to that operation, you can show that for a vector space V and a subspace W, the set V slash W of all distinct cosets of W in V, so it will form a vector space again over the same field of scalars with respect to the operations defined above. And this vector space is called, so this is your exercise, this is left as an exercise to check that this is a vector space. So you need to check all the axioms of a vector space. So this is not hard to show, very easy one. This vector space, this vector space so this vector space is called over F is called the quotient space. Quotient space of V by the subspace W. Yeah. This.